Okay, now let's talk about graphics pipelines and APIs. Really, like with every interface, I cannot teach you OpenGL syntax or any of these things. What I try to tell you about in this lecture is the high-level conceptual ideas behind OpenGL and other programming languages that are used, and APIs especially, that are used to produce graphics nowadays. So overall, there are two main types of graphics APIs. And I purposefully say APIs here because very few of them are really considered a programming language. Most of them are embedded in programming languages as an API. So you would access, you would whatever include a header or include that module and then talk to this module instead of having a dedicated graphics language. That's not really the case. Usually you would use it as an API. And there are two big types, families of APIs. One is declarative APIs and the other one are imperative. So declarative means that you have some abstract definition of scenes or something more related to how you would learn object-oriented programming. You would have objects like a camera, a cone, whatever, sphere, house, car, and all of these objects, they know about each other, so they can interact with each other. They live in a, for example, in a graph structure. So they all know about also about their own implementation more or less. So that means you can make them independent from the actual graphics commands you use to render them. So things like object knows it is a sphere and it consists of that many triangles, and this is how you draw the triangle. So this is how you would probably really relate to object-oriented programming. Examples for this are RenderMem. It's a language used by Pixar, Open Inventor, all sorts of open scene graph, also Java-related languages use these sort of languages. Very, very powerful, really. In a declarative pipeline, you would say what to render, not necessarily how. And you would build a declarative pipeline always on top of an imperative pipeline. So bits and pieces of your objects in a declarative pipeline know how to render themselves with an imperative pipeline. So in an imperative pipeline, you really know how what to render and not necessarily what. So basically, a sphere would be rendered by just being a stream of vertices with connections, like in the very first lecture when we talked about how to represent graphics objects with triangles. So it would basically just be a stream of coordinates with connectivity, and nothing really knows in that pipeline that this is a sphere. It's just rendering this stream of triangles. So we emit basically just a sequence of drawing commands and draw these points. And really, languages like OpenGL, but also PostScript, which is a printer standard and where PDF is based upon, there are languages that are imperative. You're really getting only told draw an arch here, draw a point here, and not really what these things are. So as I said, you can always build a declarative pipeline on top of an imperative model. So probably what we do mostly in this lecture are imperative models. OpenGL, in fact, more specifically, GLSL, which is a shading sub language piece of the OpenGL API. And that doesn't really matter because most of the imperative graphics pipelines look more or less similar. There used to be many more in the past when there haven't been very concrete standards yet. Currently, OpenGL is probably one of the standards, and Microsoft has its own standard, DirectX 3D, and Apple, of course, has also their own standard here and there, but they're all APIs that work approximately according to the same principles. And the same principle is always a graphics pipeline, a bit like this. You have an application stage where you emit drawing commands, where you know about your UI and what your scenes are and the order of what things are happening. And what this application stage really provides is input for your graphics pipeline. It provides a stream of graphics commands, illumination model, a camera model, a viewpoint, basically lots of hyperparameters with which you configure a relatively static graphics pipeline. There are many bits and pieces you can program inside, but the kind of order of things are more or less set in stone. And this order is usually bits and pieces we already came across, like modeling transformations, illumination, viewing transformations, clipping, we already know, the projection to screen space, scan correction, or I would call it rather rasterization, and then determining what is actually visible and what to display. So going through the individual stages, so the modeling transformation is really just to go from an object from the space where it was modeled in into an object where into a coordinate system where it can share space with other objects, right? So all of these have been transformed into a kind of static world model, but they all live in one coordinate system. Now, when I model these things, they live in their own coordinate system and are probably only individual objects. So I just put all the object spaces together into one world space. Then after having done that, I can work out local illumination. I can work out how does this light here interact with this object, and how does this reflection interact with the camera, so that you get this kind of white spot here. So I can do this relatively early at this in this pipeline, and historically that's called shading, because you can also calculate shadows in there and shades of color and shades of gray and all of these things at this stage. You do this in the entire world space basically. And next is viewing transformations. This is what we talked about mainly in the last few lectures, where we take that world space where all of our objects live in and transform it so that our camera looks down the z-axis. So here, looks down the negative z-axis and puts everything in place so that the projection to this plane here, so that I can project onto you, so that this projection on this plane gets mathematically trivial. Right, so I put everything here in place, and this is now this is my viewing transformation. So now we are ready. We still have everything in 3D coordinates, but now we are ready to execute the projection theoretically, because first I still have transformed the entire world. So first what I want to do is to clip everything away that's not relevant to me. And this is now already implemented as suggested in the last lectures, where we said, okay, we can do the clipping at 3 stages, either in world space, so somewhere here, or in clip space, where we have everything in world coordinates, or in camera coordinates, or very late when we have everything in normalized device coordinates. So in this case here, we're clipping in camera space, where this is also relatively trivial and the eye point is always in the origin. And then we can go from this clip space by executing this projection here then into normalized device coordinates. So when all of this, so these coordinates here, when I project this, they are still in camera 3D coordinates, right? They are not related at all to whatever your screen pixel coordinates are relative to the window you want to draw in. To do this step, we need to put this window basically on here and execute the linear interpolation equation from the very first lecture, where we worked out normalized device coordinates between 0 and 1. So like here. So now here we have everything in device coordinates still continuous. So this pixel position might still be at, I don't know, 10.3687 and 15.3877. That's of course something we can't address in discrete pixel space. So that needs to be converted to screen space, but it's trivial, it's a clamping operation, and we know then between 0 and 1 where to render which pixel in what color. Oh, sorry, this is just continuous. No, we don't know this yet, because for that we need the rasterization. We need to work out how fragments, how pixels, individual pixels are then actually colored to fill an object, for example, or to really map that to a discrete pixel space. And this is less trivial than it sounds like. At least it's computationally very, very expensive, because you need to do many, many millions of these operations. Also, there is a projective problem here. you need to be aware of the sorting of your objects. And there are a couple of algorithms we will discuss how to get this done, because at some point you need to work out if this green thing is in front or behind that blue triangle, and then which pixel eventually to render. And the rasterization also does interpolation for you, and we'll talk by the end of this lecture a bit about this. And then at the end of the day, it sounds ridiculous, but after having processed all of this, only then we work out what to actually render then and what's in front, so closest to the camera here. We need to wait to the very last moment to then work out what pixel color really to put on the screen. So you can see this is quite an elaborative pipeline, being, I would say, very wasteful on the way for the gain of having interactive performance with special hardware here. And this is done, you know, in interactive frame rates. So really there's a lot happening around graphics in your computer. Okay, so let's put that probably in some more numbers and some more intuitive numbers here. So what we really want to achieve here is to run this pipeline at, say, full HD, so 1920 by 1080, 60 times a second, right? At least, if I want probably a bigger frame rate and real-time performance, whatever, in a VR environment where I do this twice, then I need to do this 120 times a second and so on. So I need to do 1920 by 1080 pixels 60 times a second here, which is 124 megapixels a second. These are at least 124 times processing that entire pipeline from before per second. And that's just the output data. It's not really considering how many computations these are, because, you know, we have done all these transformations. I don't know how many vertices, how many points are in my in my overall 3D scene. So that's only possible by using specialized hardware. If you have a dedicated GPU or not, nowadays it doesn't matter. At least your CPU will have some area that is dedicated just for doing this, and rendering 3D and 2D graphics on your screen. So that was for a long time, in the early days of computer graphics, that was for a long time the biggest hurdle, until probably the 90s, when the first GPUs came up and things became feasible, rendering at these frequencies at least. So the solution is also to dumb down things. We work with very few primitives in most graphics APIs, and these primitives are usually hard-coded more or less. So you can work with points and lines and triangles, but nothing complex at all. So if you want a complex object, you need to assemble this with, for example, lots of flat triangles, with all the problems that come along with these approximations. So the GPU itself, and also part of CPU, if you have something to render, is controlled through an API like OpenGL. And certain parts of that graphics pipeline can be programmable. For example, using an OpenGL, you would use GLSL, which is the graphics language shading language, with which you build historically so-called shaders, small programs that define how your object is shaded, right? So this is part of your graphics API. So this is how you would run this pipeline in practice, and also how you run it in your coursework exercise. So that ShaderLab web interface is running exactly that pipeline, and gives you, for a few of the pieces where you can freely program the pipeline, gives you free hand, and allows you to write small programs in this GLSL language, which is essentially C with some syntactic predefinitions, priors. So you can use a few of these built-in functions basically to make your life easier as a graphics programmer. But apart from that, it's C. And that's basically what's running in the coursework framework. In the meantime, in your browser on each of your machines, even if you want on your phone, because phones are also quite powerful graphics processors. So a really, really important takeaway message for these graphics pipelines are two key stages where you're able to write small manipulation programs. And on a high level, on the probably highest level, and those are the first two that were able to be programmed, you have the Vertex stage and the Fragment stage. So if you look at the graphics pipeline more high level, we have the application stage producing application geometry graphics commands into the graphics pipeline, which produces basically the commands produce geometry, right? Protected geometry. These geometry objects in 3D are transformed to primitives like points, lines, triangles, which are rasterized into fragments. Fragments are pixel candidates. Every object is rasterized, sounds wasteful, but only a fraction of them is really ending up as a pixel. Think occlusion. If something is occluded, then everything behind it will not be rendered, but at some point you have the entire list of pixels that are on top of each other. These are called fragments. They end up in the frame buffer. The frame buffer is a dedicated, very fast memory on your GPU. And the frame buffer is then basically directly connected to your HDMI or DisplayPort or whatever cable to your monitor. So and a vertex in this context is usually a point in space defining geometry with some payload. So the payload, one mandatory payload, is the position in space. It's somewhere a point in space. There can be any other amount of other payloads, either individual parameters or three-dimensional, four-dimensional vectors. They can be color or another vector on top, or whatever you like. But they are just the nodes of geometry, the vertices. While a fragment is a sample produced during rasterization. So there are multiple fragments then which are eventually merged into a pixel. And merging can mean just taking a single one or blending them all together or doing these sort of things. And there's really a scale difference. There are only that many vertices in a scene, thousands, maybe millions. But fragments, there can be really, really a very large number. They're all the kind of pixel candidates that make up your geometry. Now, at the application stage, in a more detailed view, so we have some sort of a database where our scene is stored, somehow encoded. Usually we have that only once. That's your scene file or whatever you can load from disk. And usually you also have, especially for other graphic modes, which we will talk about later in the lecture, you have acceleration structures like hierarchies. You would save all your octrees and other kind of very efficient data structures in that way. You would run any simulations there, input event handlers, mouse interaction, these sort of things run all on the application stage. You would have any other sort of utility functions, they're all there. And also how your graphics pipeline is actually set up is set in stone and written down in the application stage. You would also generate your render area in your operating system and run then the rest of the pipeline on this single render area. So this is an example of data structure, how you can store your graphics object. So this is actually an object file, but all it says is that you have a face with a normal vector, and then the face is consists of these vertices with these coordinates, and then this face ends, and then the next face starts. So this is how this T-boot could be put together, and this is something the application stage will handle and translate into graphics commands. So the graphics pipeline has always been changing, especially in OpenGL. In OpenGL has a more kind of concrete implementation of that API. than the abstract view I just showed you. This is just an example since 3.2 and later. And usually what happened always is that more and more of these bits and pieces became programmable. So in this example here is the Vertex shader, which has its own buffers, which then writes into a stage that defines how the primitives are actually put together, where the triangles and the connectivity is defined, which then basically gives you some control per part about how you tessellate things. You can, in OpenGL, you can define things like a triangle strip, for example. And how exactly this is split up in triangles, you can actually program. And what you do with patches and vertices and so on. So if you then generate all of these, you have a representation of the entire scene with all the vertices and all this connectivity. So the geometry is then kind of complete here. At the vertex stage, I don't know yet. I only process individual vertices. I don't know the neighbors of this vertex yet. At the geometry stage, I process every primitive. So 3 vertices might make up a triangle, and my scene might completely be consistent of triangles. So the geometry shader stage knows about that. In earlier years, we had slightly different framework, not browser-based. We had the opportunity to program a little bit with the geometry shader, but this only became available since OpenGL 3.2, and current browsers do not support OpenGL 3.2 or later. They only support 1.2, so there is no geometry shading in browsers right now. And then this geometry goes through the rasterization and the interpolation and goes into the fragment shader. Really an important bit to understand here, and this is probably the key takeaway message of how to program these graphics APIs is any shader you program here is always executed in parallel. So you write a small program for one element of these lists, and this program is then executed in parallel with all the problems that come with concurrency, right? So you cannot really easily make operations in between individual threads. You would need to either do this via passes or synchronization mechanisms, which we don't go into detail in this lecture, but since this year there are provisionings in the online framework to make this actually possible. We have now multi-pass options which give you that sort of control. But really the key takeaway is the list of vertices is all processed in parallel. You write a program dealing with one vertex, and then it's executed for every single one of the vertices in your scene. Same for the fragments. Every fragment that is processed by that rasterizer is processed by your fragment stage in parallel. So this produces a long list of fragments, and all of these fragments are processed in parallel by the fragment shader stage. And this is really economies of scale, because this is massively larger as the vertex stage. So this really runs several 10,000 or sometimes millions of threads simultaneously in real time. So this is what we had before: geometry stage and rasterization stage. Vertices here, not that expensive to run all of this, to process all of these vertices, still reasonably expensive. And the rasterization stage here, which is only dealing with fragments in 2D projection space. So vertices, primitives, and then only at the very end, when the fragments are merged, we end up with pixels. So after the vertex processing, we'll find still another kind of clipping and projection fixed function or pipeline. So the vertex processing, really the vertex processing applies vertex processing to every single vertex in your scene, which is programmable. And then these things in the traditional OpenGL pipeline, they are fixed function, means you had functions to define. In the newer OpenGL pipelines, you have to program all of these things. So these are now became all shaders and much more flexible, especially in shader model 4 and later. Okay, the vertex processing is really just arbitrary vertex attributes, and the pipeline is really rigid at this point, but this is used usually to our advantage. So what you put in are vertices with certain payload parameters. So this in this case is position and color. The rasterization allows you now to interpolate between these, not only positions after the transformation, but also for, in this case here, the color, right? So you would always get a linear interpolation of the color. So this mapping here, how these are moved and mapped here to the screen space vertices, this can be programmed in the Vertex shader. Okay, for this transformation, we know already that we can use these matrices, right? We can transform from world space into camera space and then project the camera space with projection matrices on the projection plane. And historically, people always put them together to multiply them together to have more efficiency, and they gave these matrices names. So if we are in object space, world space, and multiply with the model matrix, we end up in world space where all the objects live together, right? They are now living here as one object, multiplied with object space, lives with all the other objects together in a new space. And if we multiply this with the view matrix, then we end up in view space here, where the origin is at my eye point, and I look down the z-axis. And then if I multiply this with a projection matrix, I end up with the output vertex coordinates on my plane, right? Every single pixel you see here. Now I can multiply things together, and usually the way you multiply it together, because this is usually not invertible, is that you combine the model matrix and the view matrix into the model view matrix, and then you have the projection matrix, and if you combine all three together, you have the model view projection matrix, or MVP. MVP matrix is not always the minimal viable product, but here in this case, people use the abbreviation for model view projection matrix. So I think clipping we mentioned now enough. So we are usually using this in the projection, in the clip space, view space, and then use it through the viewport transform to map as a resolution independent to normalize device coordinates so that all of my pixels have coordinates between 0 and 1. Geometry shaders, we can't do them this year, but they are quite fun pieces of equipment in your shading pipeline. What they usually, they're optional, but what they're usually used to is to help with fine detail. So you probably not ask your artists and designers to model every single leaf here on these trees or every single bump on that fish. And so this you can do procedurally with mathematical functions defined just through your geometry shader to make more, to add more details to your scene in a procedural way. So the rasterization stage, when everything is put together, all the primitives are then known and the data structures are set up, and they are all rasterized into fragments, which is again programmable, where you do fragment shaders. And then the fragment merging traditionally has been again fixed function, where you had defined what sort of blending you wanted to use for the eventually resulting fragments. But nowadays you can also program this bit, so you would either not define these functions at all and just do it in here, or you would probably abuse some of these functions and just use them for your own kind of fragment merging strategies. So in the rasterization stage, really, what happens here is primitive assembly. So you do things like backface culling. You don't need to see all the backfaces, things that point away from us. We can skip. We set up primitives for traversal, and this kind of traversal is really just sampling the objects we have here and doing at the same time interpolation. And how exactly this works, we will discuss in a separate lecture about rasterization and scan lines. Really what you need to take away now, also for the first exercises, is that you can really abuse this. If you calculate, for example, the shading component, the value, how this should be shaded here and how bright it should be relative to a light source, you can do it simply just for the vertices here, and then leave the rest to the interpolation of the rasterizer. and you'll have a kind of dense interpolation model that's called Gouraud shading, and Abhijit will talk about this in a later lecture. Yeah, and also what you can implement here or use the fixed function pipeline is the depth test and do blending. How to you probably have transparent objects. How do you put objects together to simulate transparency? So okay, one more conventional thing in computer graphics. We usually assume the lower left corner of the window, so this here, the lower left corner, as the 0, 0, 0 coordinate. So this is now 0, 0, 0, and the positive x-axis going in this direction and the positive y-axis going upwards here. And our pixels, they start at the corner, not at the center. Okay. So this is the coordinate, the lower bottom corner is the coordinate, and they mean here the pixel center here actually at 2.5, 1.5. So the sample location is here, but you would address them here with the corner. It makes no difference for you because that pixel has only one shade of color. You can't define it like that. It makes a difference for defining if that is part of an object or not. Okay, so how you fill, there are different rules for each primitive. Depends on how you set it up. Fill conventions, either you only render the wireframe or you want to fill it with shading values, illumination, local illumination, for example. That's something we talk about in a later lecture. And well, the pixels on the edge are probably the kind of questionable part. There are several algorithms to deal with these. Again, the main thing is to be consistent here. You will never have a perfect approximation here, and these pixels here are admittedly huge, so you would not really see these. What you will see is aliasing that results from these sort of undersampling artifacts. Okay, so a fragment again is a sample produced during rasterization. There can be multiple fragments coming out that would lay on top of each other on each of your potential pixels. So that's why I also use the term pixel candidates for fragments. They could end up in a pixel, but not necessarily so. So you would the vertex attributes are really just the interpolated output of the attributes of the individual nodes coming out of the vertex shader. And you can also do other things. You can apply, for example, textures. We'll talk about texture mapping in a separate lecture, but you can blend and mix together this with an image of the surface and how you would imagine this to look like, or you can use a texture to actually manipulate the appearance and the position of the nodes in the vertex shader, and then here probably how a normal vector in an illumination model is interpreted during lighting calculations. So you can really do a lot of things with the combination of the rasterizer interpolation power, and the power here is really not, it's just linear interpolation, but the power is that the rasterization unit can really do a lot of processing in parallel in a very short time. So this is a lot of power, and in combination with having this programmable. So this is a very, very powerful concept. So here you have, when you have fragments on top of each other, you need some convention of how to deal with it. Very often you would just render the one that's closer to the camera, but that is something you need to work out. For that, there is a specific algorithm called the set buffer algorithm, about which we will talk in a later lecture. But you need to work out basically what to render here and what not to render. And then eventually, when you have a frame buffer full of potential pixels, you're still not there. Your operating system might still tell you at this point that actually there's nothing to render because suddenly some other window overlap that current render area and you don't own that pixel anymore and you can't render there anymore. So bad luck, all the computation was for nothing. So the operating system might still throw away all your hard calculation works. Scissor tests and stencil tests and so on, they are tests you can use to mask out certain areas. Well, was more relevant probably in earlier times of graphics than now. But still, if it's more something you would use on operating system. The very last thing you do is now you have all these fragments. How do you blend them together, right? Translucency, or just take the closest one, for example. historically, there were more issues about things like digital to analog conversion when you had these VGA plugs. I'll not talk too much about that. It's also there is also a difference if you use an electron beam with different energy levels to activate your screen than an LCD screen. So there are different ways how these are synced. So these we won't really talk about, but the technology, the underlying technology, is vastly different from what we had just 30, 40 years ago. But the concepts are pretty much the same as back then. You want that nitty-gritty detail of the hardware as much separated from your programming concepts as possible. So you want a kind of abstract graphics unit which you tell what to render and it does it for you. And you don't want to care how exactly it does it. Display formats, there are several obsolete by now. Usually you would encode it the pixel as an RGB, and a value A defines your translucency if you want any, which is then used in a blending function to blend together, merge together with other fragments. You can encode them with 16, 32, 64 bits, just the color depth, and I think anything from here is too much for the human eye to really distinguish a difference here. Double versus single buffered, you would usually will have a double buffer system. So while the graphics pipeline runs through, one buffer is used to read out and display, and then you swap and use the other buffer to write into, and then you have a static image for the next frame. Quad buffer you would use for two eyes, right? So you have just two double buffers if you use stereo rendering, and any extra bits and pieces that are very hardware dependent. So really what I find interesting is the scale here. Geometry processing is per vertex. It does transformation and lighting. Historically, it's floating point and complex operations. There are about millions of vertices per second. And we run this through the vertex shader. The fragment processing is per fragment. We do blending, texture combinations, and historically it was fixed point and limited operations. Nowadays it's completely open and you can do whatever floating point operations you like. But the key is there are billions of fragments. So this is a gigapixel per segment or gigafragment per second operation. It's probably the most high performance computing bit in your computer right now. It does really a lot of computing, and that's probably the reason why some of your laptops get very hot when playing computer games. So the abstraction itself is implemented in a pretty interesting way. The graphics hardware is actually a shared resource, an abstract but shared resource, and what you would do is to map a user mode driver into your application, which prepares command buffers for the hardware. So this is pretty separate. The actual implementation for specific hardware is not transparent to your application layer. You would only talk to your user mode driver that provides the graphics kernel subsystem. So this gathers the access to the hardware. So you might have several graphics applications running at the same time. So this is also scheduled in here in your kernel. And on the kernel mode driver, this submits then the actual command buffer to the hardware, which has been prepared for that specific hardware. But that's something completely encapsulated in your kernel. So what kind of binary bit patterns to send as commands to your graphics hardware highly depends on the implementation and graphics hardware implementation. Actually, you will never directly code a specific type of GPU, for example. That would be a nightmare, right? If you would not be able to run a program on that has been written for whatever RTX 3060 on an RTX 3090. Yes, sure, that happens because over the generations, a card 10 years ago might not be able to run graphics code from today, but most of the basic features, like the basic hardcore, the basic rigid graphics pipeline, might still be very, very similar, especially if you use OpenGL. So you could run consistently this sort of code also on very old hardware. But only because it's abstract. You talk to a shared resource. So you would have the user, an instance of that user mode driver mapped into your OpenGL application, which talks to the graphics kernel subsystem. Then you have a kernel mode driver that assembles your command buffer for your specific graphics hardware for specific implementation. And that's something you don't never program. That's actually something you install provided by your graphics vendor. Like NVIDIA will give you installation files for their graphics driver, and they modify your operating system kernel to have this kernel mode driver installed here. Since Shader Model 4, lots of things changed, and the previously pretty rigid graphics pipeline became much more flexible. Everything became stream outputs, and everything basically became programmable. Not only became optionally programmable, but many things have been since then mandatorily programmable. So you had to program your graphics pipeline, even though you wanted to do mainly only the basic stuff of the rigid original graphics pipeline. So what low-level 3D APIs are there? Well, of course, OpenGL. This is the Open Graphics Library. This is a cross-language, cross-platform application programming interface. And you will rarely see an implementation of these. The operating systems themselves have the implementations integrated into their kernels. But what you get is, for example, just a header file or a kind of an API access, just the definition of the API, which maps directly somewhere into your operating system kernel. So you will, the API is of course open source, but you will rarely see an actual implementation of what these things do. And the actual implementations, even if you see them, are pretty boring because they do nothing else than translate your graphics commands into the specific low-level assembler language of your specific graphics hardware, and then do this for certain types and classes of hardware, whatever the vendor provides. Is basically just long lists of translations. And there's OpenGL for embedded systems. This is mainly a subset of OpenGL, which runs, is also related to WebGL, which runs in the browser coursework interface, but is also something that runs on your mobile phone, for example. DirectX Direct 3D is graphics API specifically just for Microsoft Windows, but the principle is the same, just the API commands are different. There's Vulkan. This is was initially pitched as OpenGL successor, is not anymore. OpenGL runs in parallel to it. It targets high-performance real-time 3D graphics applications, and we're not touching this in this course. It's relatively complex to program, but it's also highly efficient, much more efficient than OpenGL. So it offers a higher performance and lower CPU usage or resource usage than any other APIs. This has been designed by the Kronos group, who are setting these standards, and the pure, I think that the highest kind of principle here for Vulkan was really just performance. There's Mantle, there's a low-level graphics API by AMD. AMD, I think, moved to Vulkan, and I'm not sure actually what happened to this. Metal is the Apple thing. Apple OpenGL, basically, it's the same thing. Abstract graphics device, graphics API, which you can program in bits. And there's also Random Man, which is used by Pixar. This is an interface specific for movies. It's an open API, and it describes three-dimensional scenes and turn them into digital photorealistic images. So the purpose here, the focus here is for the realism or whatever effects you want, but not real time. So you would not use this as a real time language. It includes the random and shading language, which has a similar purpose like the graphics, the GLSL shading language. There is WebGL, which is a JavaScript API for rendering interactive 3D graphics, which is our current coursework framework. And you see how easily this transfers. I haven't really changed the individual exercises since we moved from a desktop-based implementation to the web-based implementation. The underlying principles are still exactly the same as they always have been in graphics APIs. So the probably a final word for declarative pipelines. So there are a lot of them around. Scene Graphs Performer is one, Earlicht engine, several mobile SDKs. Really, the only thing probably take away for these is they're super highly powerful, but you have them abstracted in a way as you would do conventional programming right now, right? You would probably have a star object which in its node has a rotation object which is applied to all the children in this tree. So the planet 1 and 2 here are rotated around that star, and the planets themselves have a rotation node. So they have moons perhaps that rotate around the moon. So it's all relative here. It's very straightforward to understand and relatively easy to understand. So that's probably all you need to know about this, and then you learn the library API and you can do graphics programming with declarative languages.